Greetings, viewer. Don't forget to visit my website for links to support the production of these works if you value what I'm doing. I appreciate any help you can offer. Thank you for having a look and a listen. Yours, JohnLothe. Understanding Physics, 3 volumes in 1, by Isaac Asimov. Read, recorded, and produced by JohnLothe. Chapter 7. Work and Energy. The Lever. Laws of conservation are popular with scientists. In the first place, a conservation law sets limits to possibilities. And considering a new phenomena, it is convenient to be able to rule out all explanations that would involve a violation of one of the conservation laws, at least until it is found that nothing short of a violation will do. It is then easier to work with the possibilities that remain. In addition, there is an intuitive feeling that one will not be able to get something for nothing. It therefore seems proper and orderly to suppose that the universe possesses a fixed amount of something or other, such as momentum, and that while this may be distributed among the different bodies of the universe in various ways, the total amount may neither be increased nor decreased. Consequently, if we observe a situation in which it appears that, in some respect, something is obtained for nothing, a search is quickly begun for some other factor in the situation which decreases in compensation. It may prove that it is the two factors combined in some fashion that are conserved. In the case of angular momentum, for instance, the moment of inertia can be changed at will and can seemingly be made to appear out of nowhere, or disappear into nowhere. The angular velocity, however, always changes in the opposite sense at once, and it is the product of the moment of inertia and the angular velocity that is conserved. Another case of this sort arises from a consideration of the lever. This is any rigid object capable of turning about some fixed point called the fulcrum. As a practical example, we might consider a wooden plank resting upon a sawhorse, the former being the lever, the latter the fulcrum. If the fulcrum is directly under the lever's center of gravity, the lever will remain balanced, tipping neither this way nor that. Since the lever, like any other object, behaves as though all its weight were concentrated at the center of gravity, it can then be supported as a whole on the narrow edge of the fulcrum. If the lever is of uniform dimensions and density, the center of gravity is at the geometrical center, and it is there that the fulcrum must be placed, as is the well-known children's amusement device, the seesaw. If a downward force is applied to any point on the lever, the force times the distance of its point of application from the fulcrum represents a torque. See page 75. And the lever takes on rotational motion in the direction of the torque. Suppose, though, that a downward force is at the same time applied to the lever on the other side of the fulcrum. If the second force is equal to the first and is applied at the same distance from the fulcrum, the two torques are equal in size, but not in direction. The torque on one side of the fulcrum tends to set up a clockwise rotation. The one on the other side tends to set up a counterclockwise rotation. If one torque is symbolized as tau, the other must be negative tau. The two torques add up to 0, and the lever does not move. It remains in balance. On the other hand, if the force is exerted downward on one side of the fulcrum and upward on the other, then both produce a motion in the same direction, both clockwise or both counterclockwise. The torques are then both of the same sign and add up to either 2 tau or negative 2 tau. Such a double torque is a couple, and it naturally is easier to move a lever about a fulcrum by means of a couple than by means of a single torque. It is a couple we use when we wind an alarm clock or manipulate a corkscrew. The torques used in connection with levers are often weights that are resting on the ends of the balance, or they are on pans suspended from those ends. We can say that two equal weights will leave a lever in balance if they are placed on opposite sides of the fulcrum and at equal distances from it. This, in fact, is the principle of the balance. A balance has two pans of equal weight suspended from the ends of a horizontal rod that pivots about a central fulcrum. If an object of unknown weight is placed in one pan, combinations of known weights can be put in the other till the two pans balance. We then know that the unknown weight is equal to the sum of the known weights in the other pan. As explained on page 57, this actually serves to measure mass as well as weight. Because of its use in the balance, a lever subjected to equal and opposite torques is said to be in equilibrium, from Latin words meaning equal weights. And this expression has come to be applied to any system under the stress of forces that produce effects that cancel out and leave the overall condition unchanged. For a lever to be in equilibrium, it must be subjected to equal and opposite torques, and this may be true even if the forces applied are unequal. Consider a downward force, F, applied on one side of a lever at a given distance, R, from the fulcrum. The torque would be F times R, or downward force, times a given distance. Next, consider a downward force twice as large, 2F, applied to the other side of the fulcrum, but at a distance only half that of the first. Negative R divided by 2. The distance is here given a negative sign because it is in the opposite direction from the fulcrum as compared with the first. This second torque is 2F by negative R divided by 2, or negative F times R. The two torques are equal and opposite, and the lever remains in equilibrium. If the forces are produced by unequal weights resting on the ends of the lever, it is easy to see that the center of gravity of the system must shift toward the end with the greater weight to maintain equilibrium. The fulcrum must be directly under the new position of the center of gravity. When this is done, it will be found that its position is such that the product of one weight at its distance from the fulcrum will be equal to the product of the other and its distance from the fulcrum. Thus, if two children of roughly equal weight are on a seesaw, they are right to sit at the ends. If one child is markedly heavier than the other, he should sit closer to the fulcrum. The two should so distribute themselves, in fact, that their own center of gravity plus that of the seesaw remains directly above the fulcrum. It is also possible, in the case of some seesaws, to shift the board and adjust the position of the fulcrum. Because of the fact that torques rather than forces must be equal in order to produce equilibrium, a lever can be put to good use. Suppose a 250 kilogram weight, equivalent to a force of about 2,450 newtons, is placed 1 meter from the fulcrum. Next, suppose that 10 meters from the fulcrum, on the other side of the lever, a man applies a downward force of 245 newtons, the equivalent of a 25 kilogram weight. The torque associated with the force, 25 times 10, is equal and opposite to that of the torque produced by the weight on the other side of the lever, 250 times 1. The lever is then placed in equilibrium, and the heavy weight is supported by the lighter force. If the man applies a somewhat greater force, one that is still considerably less than that produced by the weight on the other side, the lever overbalances on his own side. A man is not so much conscious of torque as of force, more exactly of muscular effort. He knows that he cannot apply sufficient force directly to the 250 kilogram weight to lift it. By making use of the lever, however, he can do the job with a force 1/10 that required for direct lifting. By adjusting the differences properly, he can make do with a force 1/100th, 1/1000th, or indeed any fraction of that required for direct lifting. The usefulness of the lever as a method of multiplying man's lifting ability is evidenced by the very word lever, which comes from a Latin word meaning to lift. No doubt, even primitive man had stumbled upon this principle of the lever, but it was not until the time of the Greek mathematician Archimedes, 287 to 212 BC, that the situation was analyzed scientifically. So well did Archimedes appreciate the principle of the lever and its use in unlimited multiplication of force that he said with pardonable bombast, "Give me a place to stand on, and I will move the world." Any device that transfers a force from the point where it is applied to another point where it is used is a machine, from a Latin word meaning invention or device. The lever does this since a force applied on one side of the fulcrum can lift a weight on the other side. It does this in so uncomplicated a fashion that it cannot be further simplified. It is therefore an example of a simple machine. Other examples of simple machines are the inclined plane, the wheel and axle. Some add 3 other simple machines to the list: the pulley, the wedge, and the screw. However, the pulley can be viewed as a sort of lever. The wedge consists of 2 inclined planes set back to back, and the screw is an inclined plane wound about an axis. Virtually all the more complicated machines devised and used by mankind until recent times have been merely ingenious combinations of 2 or more of these simple machines. These machines depend upon the motions and forces produced by moving bodies through direct contact. As a result, that branch of physics that deals with such motions and forces is called mechanics. That branch of mechanics that specifically deals with motion is called dynamics, while that branch that deals with motions in equilibrium is called statics, from a Greek word meaning to cause to stand. Archimedes was the first great name in the history of statics because of his work with the lever. Galileo, of course, was the first great name in the history of dynamics. One force that does not seem to be the result of direct contact of one body upon another is gravitation. Gravitation seemingly exerts a force from a distance and produces a motion without involving direct contact between bodies. Such action at a distance troubled Newton and many physicists after him. Expedients were worked out to explain this away, and gravitation was included among the mechanical forces. Thus, the study of the motions of the heavenly bodies that result from and are controlled by gravitational forces is called celestial mechanics. Multiplying force. A machine not only transfers a force, it can often be used to multiply that force, as in the example of the lever described above. Yet this multiplication of force should be approached with suspicion. How can 1 Newton of force do the work of 10 Newtons just by transmitting it through a rigid bar? Such generosity on the part of the universe is too much to expect, as I pointed out at the beginning of the chapter. Something else must be lost to make up for it. If we consider the lever lifting the 250 kilogram weight by use of a force equivalent to only 25 kilograms of weight, we can see in the accompanying diagram that we have 2 similar triangles. The sides in altitude of one are to the corresponding sides in altitude of the other, as the distance of the weight from the fulcrum is to the distance of the applied force from the fulcrum. In other words, if we apply a force at a point 10 times as far from the fulcrum as the weight is, then, to lift the weight a given distance, we must push down through a distance 10 times as great. There is the answer. In lifting a weight by means of a lever, we may adjust distances from the fulcrum in such a way as to make use of a fraction of the force that would be required without the lever. But we must then apply that fractional force through a correspondingly greater distance. The product of the force multiplied by the distance remains the same at either end of the lever. This turns out to be true of any machine that seems to multiply a force. The smaller force performs the task that would require a larger force without the machine, but always at the cost of having to be exerted through a correspondingly longer distance. The product of force and distance in the direction of the force is called work, and is usually symbolized as W, so that W equals F times D, or work equals force times distance. Equation 7-1. In a sense, work is an unfortunate term to use in this connection. Anyone will agree that lifting a weight through a distance is work, but in the common use of the term, matters are not confined to this alone. In the common language, work is a term applied to the product of any form of exertion. To sit quietly in my chair for half an hour and think of what I am going to say next in this book may strike me as being hard work, but it involves no action of a force through a distance and is not work to a physicist. Again, to stand in one place and hold a heavy suitcase seems hard work, but since the suitcase doesn't move, no work is being done on it. If one walks along with a suitcase, there is still no work being done on it, for although it is moving horizontally, it is not moving in the direction of the vertical force that keeps it from falling. Nevertheless, the term work, signifying a force multiplied by the distance through which a body moves in the direction of the force, is ineradicably established and must be accepted. The units of work are those of force multiplied by those of distance. In the MKS system, the unit of work is the Newton meter, and this is named the joule, pronounced joule after an English physicist, whom I will have occasion to mention later. In the CGS system, the unit of work is the dyne centimeter, which is called ERG, from a Greek word meaning work. Since a Newton is equal to 100,000 dynes and a meter to 100 centimeters, a Newton meter is equivalent to 100,000 times 100 dyne centimeters. In other words, 1 joule is equal to 10 million ERGs. Since force is a vector quantity, it might seem that work, which is after all the product of a force and a distance, might also be a vector, and that one might speak of a given amount of work to the right and the same amount of work to the left as being equal and opposite. This is not so, however, as we will find if we consider the units of work once more. A Newton is defined as a kilogram meter per second, or kgm divided by second squared. If a joule is a Newton meter, then it is also a kilogram meter per second, or a kgm squared second squared. This last can be written kg meter per second squared. But m per second, meters per second, is a unit of velocity, and this means that the unit of work is equal to the unit of mass times the square of the unit of velocity, or work equals mass times velocity squared. W equals m times v squared. It is true that velocity is a vector quantity. Therefore, one might speak of negative velocity and positive velocity. But the unit of work involves the square of the velocity. The square of a positive number, positive velocity by positive velocity, and the square of a negative number, negative velocity by negative velocity, are both positive velocity squared, as we know from elementary algebra. Consequently, the square of the velocity involves no differences in signs, and a unit that includes the square of the velocity is not a vector unit, unless it contains vector units other than velocity, of course. We conclude, then, that work is a scalar quantity. Returning to the lever, we see that the work involved in raising a boulder with a lever is the same as that involved in raising a boulder without a lever. but that the distribution of work between force and distance differs. The same is true where an inclined plane is the device used. Let us say it is necessary to raise a 50-kilogram barrel through a height of 2 meters onto the back of a truck. Since a kilogram of weight exerts a downward force of 9.8 newtons, a total upward force of 490 newtons is required to lift the barrel. To exert 490 newtons of force through a distance of 2 meters in the direction of the force is to do 980 joules of work. Suppose instead that we lay a sloping plank from the ground to the truck so that the plank makes an angle of 30 degrees with the ground. Under those conditions, the length of the plank from ground to truck is just twice the vertical height from ground to truck, or 4 meters. The force required to roll the barrel up the plank is 295 newtons, just half the force required for direct lifting. That half force is exerted through double distance, however, and 980 joules of work is still done. The gentler the slope of the inclined plane, the smaller the force required to move the barrel, and the longer the distance through which it must be moved. The inclined plane dilutes force, as it diluted velocity for Galileo. By diluting gravitational force, see page 10. Neither the inclined plane, nor the lever, nor any machine dilutes work. If we stick to work rather than force, we never get something for nothing. But if we gain nothing on work, why bother? The answer is that even if we gain nothing directly, we may gain by altering the distribution between force and distance. If it is a question of lifting, by our unaided effort, 250 kilograms, 2 meters directly upward, we must give up. We cannot lift it a meter, a centimeter, or anything at all. We cannot budget. To move the equivalent of 50 kilograms through 10 meters is possible, however, especially if we work slowly. In this way, we can do the same work, 50 times 10. That would have been impossible under the previous conditions, 250 times 2. To lift the equivalent of 5 kilograms through 100 meters may be tedious, but it is quite easy. Again, if we were asked to shinny up a rope suspended from the roof of a 5-story building, we might well decide it to be beyond our capacity unless we were in excellent physical shape. However, a quite ordinary man can lift his weight to a 5th-story roof if he goes up by way of a ramp, which is an inclined plane that enables him to use less force to lift his body at the expense of moving it through a longer distance. It is sometimes convenient to do the opposite, expend extra force in order to gain distance. Thus a great deal of force is exerted upon the pedals of a bicycle. This is transmitted to a point on the rear wheel near the hub. The spoke of the wheel then act as levers, with the hub the fulcrum. So a much smaller force is applied to the rim of the wheel, which, however, moves through a correspondingly larger distance. The bicycle is therefore a machine that enables the body to convert force into distance, without changing the total work done, more efficiently than it could without the bicycle. It is for this reason that a man on a bicycle can easily outrace a running man, although both are using their leg muscles with equal effort. The definition of work as the product of a force and the distance through which it acts says nothing about the time it takes to act. Men usually find it preferable to accomplish a particular amount of work in a short time rather than in a long time, and are therefore interested in the rate at which work is done. This rate is spoken of as power. The units of power are joules per second in the MKS system and ERGs per second in the CGS system. A very common unit of power which fits into neither system was originated by the Scottish engineer James Watt, 1736 to 1819. He had improved the steam engine and made it practical toward the end of the 18th century, and he was anxious to know how its rate of work in pumping water out of coal mines compared with the rate of work of the horses previously used to operate the pumps. In order to define a horsepower, he tested horses to see how much weight they could lift through what distance and in what time. He concluded that a strong horse could lift 150 pounds through a height of 220 feet in 1 minute. So 1 horsepower was equal to 150 times 200 divided by 1, or 33,000 foot-pounds per minute. This inconvenient unit is equal to 745.2 joules per second, or 7,452,000,000 ERGs per second. A joule second is defined as a watt in James Watt's honor, and so we can also say that 1 horsepower is equal to 745.2 watts. The watt, however, is most commonly used in electrical measurements. In mechanical engineering, at least in Great Britain and the United States, it is still horsepower all the way. The power of our automobile engines, for instance, is routinely given in horsepower. Mechanical energy. It is neat and pleasant to see that the work put into one end of a lever is equal to the work coming out of the other end, and we might fairly suspect that there was such a thing as conservation of work. Unfortunately, such a possible conservation law runs into a snag almost at once. After all, where did the work come from that was put into the lever? If one end of the lever was manipulated by a human being who was using the lever to lift a weight, the work came from that done by the moving human arm. And where does the work of the moving arm come from? A man sitting quietly can suddenly move his arm and do work where no work had previously seemed to exist. This runs counter to the notion of conservation, in which the phenomena, being conserved, can be neither created nor destroyed. If one is anxious to set up a conservation law involving work, therefore, one might suppose that work, or something equivalent to work, could be stored in the human body, and perhaps in other objects, and that this work store could be called upon at need and converted into visible, palpable work. At first blush, such a work store might have seemed to be particularly associated with life, since living things seem filled with this capacity to do work, whereas dead things, for the most part, lay quiescent and did not work. The German philosopher and scientist Gottfried Wilhelm Leibniz, 1646 to 1716, who was the first to get a clear notion of work in the physicist's sense, chose to call this work store vis viva, Latin for living force. However, it is clearly wrong to suppose that work is stored only in living things. As a matter of fact, the wind can drive ships, and running water can turn millstones, and in both cases, force is being exerted through a distance. Work, then, was obviously stored in inanimate objects as well as in animate ones. In 1807, the English physician Thomas Young, 1773 to 1829, proposed the term energy for this work store. This is from Greek words meaning work within, and is a purely neutral term that can apply to any object, living or dead. This term gradually became popular and is now applied to any phenomena capable of conversion into work. There are many varieties of such phenomena, and therefore many forms of energy. The first form of energy to be clearly recognized as such, perhaps, was that of motion itself. Work involved motion, since an object had to be moved through a distance. So it was not surprising that motion could do work. It was moving air or wind that drove a ship, and not still air. Moving water that can turn a millstone, and not still water. It was not air or water that contained energy then, but the motion of the air or water. In fact, anything that moved contained energy, for if the moving object, whatever it was, collided with another, it could transfer its momentum to that second object and set its mass into motion. It would thus be doing work upon it, for a mass would have moved through a distance under the urging of a force. The energy associated with motion is called kinetic energy, a term introduced by the English physicist Lord Kelvin, 1824 to 1907, in 1856. The word kinetic is from a Greek word meaning motion. Exactly how much kinetic energy is contained in a body moving at a certain velocity, v. To determine this, let us assume that in the end we are going to discover that there exists a conservation law for work in all its forms, stored and otherwise. In that case, we can be reasonably confident that if we find out how much work it takes to get a body moving at a certain velocity, v, then that automatically will be the amount of work it can do on some other object through its motion at that velocity. In short, that would be its kinetic energy. To get a body moving, in the first place, takes a force, and that force, by Newton's second law, is equal to the mass of the moving body multiplied by its acceleration. F equals m times a. The body will travel for a certain distance, d, before the acceleration brings it up to the velocity, v, which we are inquiring into. The work done on the body to get it to that velocity is the force multiplied by the distance. Expressing the force as m times a, we have work equals mass times acceleration times distance, or W equals m times a times d, equation 7-2. Now, much earlier in the book, in discussing Galileo's experiments with falling bodies, we showed that v equals a times t, or velocity equals acceleration times time. That velocity, in other words, is the product of acceleration and time. This is easily rearranged to t equals v divided by a, or time equals velocity divided by acceleration. We also pointed out in discussing Galileo's experiments that where there is uniform acceleration, distance equals 1/2 the acceleration times time squared, where d is the distance covered by the moving body. If in place of time in the relationship just given, the quantity velocity divided by acceleration is substituted, we have distance equals 1/2 the acceleration times velocity divided by acceleration squared equals 1/2 velocity squared divided by acceleration. Equation 7-3. Let us now substitute this value for d in equation 7-2, which becomes work equals 1/2 times the mass times the acceleration times velocity squared divided by acceleration equals 1/2 times mass times velocity squared. Equation 7-4. This is the work that must be done upon a body of mass, m, to get it to move at a velocity, v, and it is therefore the kinetic energy contained by the body of that mass and with that velocity. If we symbolize kinetic energy as Ek, we can write Ek equals 1/2 times m times v squared, or the kinetic energy is equal to 1/2 times the mass times the velocity squared. Equation 7-5. I have already pointed out that work has the units of mass multiplied by those of velocity squared, and, as is clear from equation 7-5, so has kinetic energy. Therefore, kinetic energy can be measured in joules or ERGs, as can work. Indeed, all forms of energy can be measured in these units. We might now imagine that we can set up a conservation law in which kinetic energy can be converted into work and vice versa, but in which the sum of kinetic energy and work in any isolated system must remain constant. Such a conservation law will not, however, hold water, as can easily be demonstrated. An object thrown up into the air has a certain velocity, and therefore a certain kinetic energy as it leaves the hand, or the catapult, or the cannon. As it climbs upward, its velocity decreases because of the acceleration imposed upon it by the Earth's gravitational field. Kinetic energy is therefore constantly disappearing, and eventually, when the ball reaches maximum height and comes to a halt, its kinetic energy is zero, and has therefore entirely disappeared. One might suppose that the kinetic energy has disappeared because work has been done on the atmosphere, and that therefore kinetic energy has been converted into work. However, this is not an adequate explanation of events, for the same thing would happen in a vacuum. One might next suppose that the kinetic energy had disappeared completely and beyond redemption without the appearance of work, and that no conservation law involving work and energy was therefore possible. However, after an object has reached maximum height and its kinetic velocity has been reduced to zero, it begins to fall again, still under the acceleration of gravitational force. It falls faster and faster, gaining more and more kinetic energy, and when it hits the ground, neglecting air resistance, it possesses all the kinetic energy with which it started. Rather than lose our chance at a conservation law, it seems reasonable to assume that energy is not truly lost as an object rises upward, but that it is merely stored in some form other than kinetic energy. Work must be done on an object to lift it to a particular height against the pull of gravity. Even if once it has reached that height, it is not moving. This work must be stored in the form of an energy that it contains by virtue of its position with respect to the gravitational field. Kinetic energy is thus, little by little, converted into energy of position as the object rises. At maximum height, all the kinetic energy has become energy of position. As the object falls once more, the energy of position is converted back into kinetic energy. Since the energy of position has the potentiality of kinetic energy, the Scottish engineer William J. M. Rankine, 1820 to 1872, suggested in 1853 that it be termed potential energy, and this suggestion was eventually adopted. To lift a body a certain distance, d, upward, a force equal to its weight must be exerted through that distance. The force exerted by a weight is equal to m times g, where m is mass and g the acceleration due to gravity. See equation 5-1 on page 54. If we let potential energy be symbolized as EP, then we have EP equals m times g times d, or potential energy equals mass times gravity times distance. Equation 7-6. If all the kinetic energy of a body is converted into potential energy, then the original EK is converted into an equivalent EP, or, combining equations 7-5 and 7-6, we have 1/2 times the mass times the velocity squared equals mass times gravity times distance, or 1/2 times m times v squared equals m times g times d. Or simplifying and assuming g to be constant, v squared equals 2 times g times d equals 19.6 times d. Or velocity squared equals 2 times gravity times distance equals 19.6 times distance. Equation 7-7. From this relationship, one can calculate, neglecting air resistance, the height to which an object will rise if the initial velocity with which it is propelled upward is known. The same relationship can be obtained from the equations arising out of Galileo's experiments with falling objects. Kinetic energy and potential energy are the types of energy made use of by machines built up out of levers, inclined planes, and wheels, and the two forms may therefore be lumped together as mechanical energy. As long as the time of Leibniz, it was recognized that there was a sort of conservation of mechanical energy, and that if such extraneous factors as friction and air resistance were neglected, mechanical energy could be visualized as bouncing back and forth between the kinetic form and the potential form, or between either and work, but not taken in all three forms, as appearing from nowhere or disappearing into nowhere. The conservation of energy. Unfortunately, the law of conservation of mechanical energy, however neat it might seem under certain limited circumstances, has its imperfections, and these at once throw it out of court as a true conservation law. An object hurled into the air with a certain kinetic energy returns to the ground without quite the original kinetic energy. A small quantity has been lost through air resistance. Again, if an elastic object is dropped from a given height, it should, if mechanical energy is to be truly conserved, bounce and return to exactly its original height. This it does not do. It always returns to somewhat less than the original height, and if allowed to drop again and bounce, and drop again and bounce, it will reach lower and lower heights until it no longer bounces at all. Here, it is not only the air resistance that interferes, but also the imperfect elasticity of the body itself. Indeed, if a lump of soft clay is dropped, its potential energy is converted to kinetic energy, but at the moment it strikes the ground with a non-bouncing splat, that kinetic energy is gone, and without any reformation of potential energy. To all appearances, mechanical energy disappears in these cases. One might argue that these losses of mechanical energy are due to imperfections in the environment. If only a frictionless system were imagined in a perfect vacuum, if all objects were completely elastic, then mechanical energy would be conserved. However, such an argument is quite useless, for in a true conservation law, the imperfections of the real world do not affect the law's validity. Momentum is conserved, for instance, regardless of friction, air resistance, imperfect elasticity, or any other departure from the ideal. If we still want to seek a conservation law that will involve work, we must make up our minds that for every loss of mechanical energy, there must be a gain of something else. That something else is not difficult to find. Friction, one of the most prominent imperfections of the environment, will give rise to heat, and if the friction is considerable, the heat developed is likewise considerable. The temperature of a match head can be brought to the ignition point in a second by rubbing it against a rough surface. Conversely, heat is quite capable of being turned into mechanical energy. The heat of the sun raises countless tons of water vapor kilometers high into the air, so that all the mechanical energy of falling water, whereas rain, cataracts, or quietly flowing rivers, must stem from the sun's heat. Furthermore, the 18th century saw man deliberately convert heat into mechanical energy by means of a device destined to reshape the world. Heat was used to change water into steam in a confined chamber, and this steam was then used to turn wheels and drive pistons. Such a device is, of course, a steam engine. It seemed clear, therefore, that one must add the phenomena of heat to that of work, kinetic energy and potential energy, in working out a true conservation law. Heat, in short, would have to be considered another form of energy. But if that is so, then any other phenomena that could give rise to heat would also have to be considered a form of energy. An electric current can heat a wire, and a magnet can give rise to an electric current, so both electricity and magnetism are forms of energy. Light and sound are also forms of energy, and so on. If the conservation law is to encompass work and all forms of energy, not mechanical energy alone, then it had to be shown that one form of energy could be converted into another quantitatively. In other words, in such energy conversions, all energy must be accounted for. No energy must be completely lost in the process. No energy created. This point was tested thoroughly over a period of years in the 1840s by an English brewer named James Prescott Joule, 1818 to 1889, whose hobby was physics. He measured the heat produced by an electric current, that produced by the friction of water against glass, by the kinetic energy of turning paddle wheels in water, by the work involved in compressing gas, and so on. In doing so, he found that a fixed amount of one kind of energy was converted into a fixed amount of another kind of energy, and that if energy in all its varieties was considered, no energy was either lost or created. It is in his honor that the unit of work and energy in the MKS system is named the joule. In a more restricted sense, one can consider that Joule proved that a certain amount of work always produced a certain amount of heat. Now, the common British unit of work is the foot-pound. That is, the work required to raise 1 pound of mass through a height of 1 foot against the pull of gravity. The common British unit of heat is the British thermal unit, commonly abbreviated BTU, which is the amount of heat required to raise the temperature of 1 pound of water by 1 degrees Fahrenheit. Joule and his successors determined that 778 foot-pounds are equivalent to 1 BTU, and this is called the mechanical equivalent of heat. It is preferable to express this mechanical equivalent of heat in the metric system of units. A foot-pound is equal to 1.356 joules. So 778 foot-pounds equal 1,055 joules. Furthermore, the most common unit of heat in physics is the calorie, which is the amount of heat required to raise the temperature of 1 gram of water by 1 degrees centigrade. Footnote. There will be more to say about Fahrenheit degrees, centigrade degrees, calories, and other items of the sort later in the book. See chapters 13 and 14. 1 BTU is equal to 252 calories. Therefore, Joule's mechanical equivalent of heat can be expressed as 1,055 joules equal 252 calories, or 4.18 joules equal 1 calorie. Once this much was clear, it was a natural move to suppose that the law of conservation of mechanical energy should be converted into a law of conservation of energy. In the broadest sense of the word, including under energy, work, mechanical energy, heat, and everything else that could be converted into heat. Joule saw this, and even before his experiments were far advanced, a German physicist named Julius Robert von Meyer, 1814 to 1878, maintained it to be true. However, the law was first explicitly stated in form clear enough and emphatic enough to win acceptance by the scientific community in 1847 by the German physicist and biologist Hermann von Helmholtz, 1821 to 1894, and it is he who is generally considered the discoverer of the law. The law of conservation of energy is probably the most fundamental of all the generalizations made by scientists, and the one they would be most reluctant to discard. As far as we can tell, it holds through all the departures of the real universe from the ideal models set up by scientists. It holds for living systems as well as non-living ones, and for the tiny world of the subatomic realm as well as for the cosmic world of the galaxies. At least twice in the last century, phenomena were discovered which seemed to violate the law, but both times physicists were able to save matter by broadening the interpretation of energy. In 1905, Albert Einstein showed that mass itself was a form of energy, and in 1931, the Austrian physicist Wolfgang Pauli, 1900 to 1958, advanced the concept of a new kind of subatomic particle, the neutrino, to account for apparent departures from the law of conservation of energy. Nor was this merely a matter of saving appearances, or of patching up a law that was springing leaks. Each broadening of the concept of conservation of energy fit neatly into the expanding structure of 20th century science and helped explain a host of phenomena. It also helped predict, accurately, another host of phenomena that could not have been explained or predicted otherwise. The nuclear bomb, for instance, is a phenomena that can only be explained by the Einsteinian concept that mass is a form of energy. If you enjoyed this recording, you can find more and support the production of these works at my website, JohnLothe.wordpress.com. That's www.JohnLothe.wordpress.com. Thanks for having a look and a listen. Your friend, John Lothe.